Dear students, in the last lecture we have studied about the analysis of symmetrical fold. In this lecture we have discussed the method for the analysis of the symmetrical fold. Unbalanced system operation result of due to unsymmetrical fold is that line to ground fault or line to line fault. System operation may also become unbalanced when loads are unbalanced, as in the presence of large single phase load. So whenever the system will unbalance, then how we can study, we can analyze that system. So for to analyze these types of system, either we have to analyze on the three phase basis, means we have to study all the three phase, or a more convenient method for analyzing of unbalanced operation is through the symmetrical component, where three phases voltage which may be unbalanced are transformed into set of balanced voltage called the symmetrical component. So for the analysis of unsymmetrical fold, an unbalanced system will be converted into the balanced system, and this conversion is known as the symmetrical component transformation. So before studying about the unsymmetrical fold analysis, we have to study about the symmetrical component transformation. So first, we assume a set of balanced voltage VA, VB, VC, which is characterized by equal magnitude and interface difference of 120 degree. This is the definition of the balanced voltage which we have studied earlier, that VA, VB, VC has all three phases are equal magnitude and the phase difference of 120 degrees, such that phase A is that VB lags VA by 120 degree and VC lags VB by 120 degree, or we can say the sequence is like that A, B and C. So whenever we will study the electrical machine, we will study, by default we have studied the positive sequence component or positive phasor. So if we have write the expression in the mathematical form for this balanced system, we can say that VA will equal to the VA, VB equal to the alpha square VA and VC equal to the alpha VA. Means we have write the expression of VB and VC in terms of VA, which we can say it is a reference phasor VA, and alpha is the e raised to power j 120 degree. Alpha is the mathematical operator which is basically used for the which is basically denote the phase difference. VB is equals to alpha square VA, because the alpha is e raised to power j 120 degree. So alpha square is e raised to power j 240, or we can say e raised to power minus j 120. So VA, we can say that the VB lags VA by 120 degree. Similarly, if we can see that the alpha square is equal to e raised to power j 240, or e raised to minus j 120, or we can say alpha square will become the alpha conjugate. Similarly, other expression can also be right here, alpha square conjugate. Then we can say alpha square is the alpha conjugate, and conjugate, then again conjugate, then it will become alpha. Alpha cube is equal to alpha square dot alpha. Alpha square is the alpha conjugate and alpha. So alpha conjugate and alpha will become 1. So alpha cube, the value of alpha cube will become 1. And one more expression, 1 plus alpha square will become 0. You can check it by putting the values. So this is the about the alpha operator. Now we come again our sequence component. So if the phase sequence is ACB, means if we change any two phases, if we interchange any two phases, then the phase sequence will become ACB, or we can say it is a negative sequence component. In that case, VB will become VA will become VA, VB will become alpha VA, and VC become alpha square VA. So this is the definition of the positive and negative sequence component. By default, we have studied only the positive sequence case. We never studied in the machine about the negative sequence case. Basically, if the sequence is A, B, C, it is called positive sequence, and if the sequence is A, C, B, then it is called negative sequence. Suffix 1 is commonly used for the positive sequence, and suffix 2 is used for the negative sequence. So we can say that if positive sequence component will become VA1, VB1 equal to the alpha square VA1, and VC1 equal to the alpha VA1. Suffix 2 is used for the negative sequence component. VA2, VB2 will become alpha VA2, and VC2 become alpha square VA2. Another set of balanced voltage is known as a zero sequence component, where if all the three phases are connected to a single wire, or then the magnitude of VA, VB, VC will become equal, but the phase difference of 0 degree. Then this set of voltages is known as a zero sequence component, or we can say it is denoted by the suffix 0. VA naught, VB naught equal to the VA naught, and VC naught equal to the VA naught. Now, till now we have given the definition of positive, negative, zero sequence component. Now we have discussed a theorem which is known as the Fortescue theorem, which is you have already studied in the subject measurement. So according to the Fortescue theorem, any unbalanced phasor, three-phase phasor, may be expressed as the sum of positive, negative, and zero sequence component. So according to the Fortescue theorem, an unbalanced phasor of voltage VA, VB, VC can be expressed as a sum of positive, negative, and zero sequence component, or we can say that VA equal to the VA1 plus VA2 plus VA0, VB equal to the VB1 plus VB2 plus VB0, and VC equal to the VC1 plus VC2 plus VC0. Here VA, VB, VC, this VA, VB, VC are the unbalanced phasor, while VA1, VB1, VC1 it is the balanced phasor. VA2, VB2, VC2 is the balanced phasors, and VA0, VB0, and VC0 it is also the balanced phasor, or we can say that we have converted an unbalanced voltages phasor into the balanced voltage components. So this can be also expressed as the phasor diagram. This is VA1, VB1, and VC1. So VB1 equal to the alpha square VA1 means minus of 120 degree, because VC1 equal to the alpha VA1. So the angle is right down in the anti-clockwise direction. Similarly, VA2, then VB2, and then VC2, VA0, VB0, VC0. So these three sets are the balanced set. Now if we add VA1, then VA1 plus VA2 plus VA0. So according to Fortescue theorem, it will become equal to the VA. So we draw the VA. Similarly, VB1, we add VB1 and VB2, then VB0. So according to the Fortescue theorem, it will become VB. Similarly, VC. So we can say from the phasor diagram that VA, VB, VC are mutually unbalanced, or we can say these are unbalanced system of voltage. But if we resolve it into the three parts, then these three parts are the balanced phasor. So if we replace VA1, VA2, VA0 in terms of VA, then the VA equal to become VA plus VA2 plus VA0. VB become alpha square VA1 plus alpha VA2 plus VA0. VC will become alpha VA1 plus alpha square VA2 plus VA0. We can arrange in the matrix form, then VA, VB, VC will become 1, 1, 1, 1, alpha square alpha, alpha square VA1, VA2, VA0, or we can write it as a VP is equals to AVS, where a VP is the phasor component and Vs will become the sequence component. Va1, Va2, Va0 is the positive, negative sequence and zero sequence voltages phasor. Va, Vb, Vc are the phase vector of original phase Vp. So, and A is a constant whose value is 1, 1, 1, alpha square alpha 1, alpha square 1. If we want to calculate the Vs, then we can write Vs is equals to A inverse Vp. The value of A inverse can be calculated from the value of A, whose value is 1 by 3, 1 alpha square, 1 alpha square alpha, 1, 1, 1. This is the value of A inverse. And if we want to write the expression of Va1, Va2, Va0 in terms of Va, Vb, Vc, then Va1 will become 1 by 3 of Va1 plus alpha Vab plus alpha square Vc. Va2 will become 1 by 3 Va plus alpha square Vb plus alpha Vc, and Va0 will become 1 by 3 Va plus Vb plus Vc. So this is basically the conversion of phase component to the sequence component. If in the question the phase component is given, then we can calculate the sequence component Va1, Va2, Va0. Similarly, if the sequence component is given, we can calculate the phase component as well. This symmetrical component transformation given above in terms of voltage can apply for any set of phasor that for the consider IEP is equal to AIS or IS is equal to A inverse IP. So this is all about the symmetrical component transformation, and from the next class we will discuss the unbalanced fault analysis. Thank you.